We've been spending these series of videos applying what we've learned before about motion to things that are rotating. We looked at forces for things that are rotating, that's torque. We looked at inertia, how that applies, how that translates to rotating things. We also looked at energy. In this video, we're looking at momentum. How do we apply the idea of momentum to rotational motion? So this is the momentum for rotating things, also known as the angular momentum. We're also going to touch upon impulse, remind ourselves about that link between torque, time, and momentum, and we'll look at something known as conservation of momentum. So let's dive right in. First, the basics of momentum. All right, we're going to look at cousins. When we were first introducing momentum for things moving in straight lines, we learned that momentum is based on the inertia of the object multiplied by its velocity. This is our translational version. So momentum, which was given the letter P, is equal to m times v, inertia times velocity. Well, if I have something that's rotating, it also has momentum, angular or rotational momentum. All right, the angular momentum equation, it's again cousins. It must rely on inertia and velocity. Now, the symbol we use for angular momentum is uppercase letter L, which is a little weird. It doesn't really match any of our letters that are in the name. But uppercase letter L, the inertia for rotating things is that that rotational inertia, uppercase letter I, same I that we learned about prior. And what's the cousin for velocity? Well, it's angular velocity. So very straightforward. We're not going to derive it. There's no need to do that. But angular momentum is based on I times omega. To be honest, it's pretty seldom that you're just going to do a straight calculation of angular momentum. But if you did, the units you would use is kilograms meters squared per second. You might be wondering how I get those units since our angular motion is usually described in radians per second. It's really just coming from the idea that, if you remember, angular momentum is V over R. So if we're looking at the units right here, if I was switching to red, and again, this isn't important. The AP exam isn't going to tell you. I is going to be mass, kilograms, times radius squared, so times meters squared. We won't worry about the coefficient. It wouldn't have units. And then times omega. That would be speed, meters over seconds, m over s, divided by r, divided by meters. So I have a whole bunch of these meters. This meter is going to cancel out with this meter. I still have meters squared. I still have kilograms. I still have seconds. So that's how I get those kilogram meters squared per second. So weird units, but again, for the most part, you're not really just going to do on the AP exam straight up calculations. But this is the idea. This is what angular momentum is. So moving right along, angular impulse. We learned about impulse for translational motion. The force multiplied by time gives us delta P. This is actually where we saw momentum pop up from when we applied this equation. So this right here is the change in momentum. Well, same thing applies. The cousin of force is torque, still have time, that's the same thing. We're going to get, when we have a torque acting on an object for a certain period of time, a change in angular momentum. An L minus L naught, change in. One minus the other, L minus L naught. And if you remember, there were graphs for impulse. Before it would be F versus T, but here it's going to be torque versus time. Do you remember if I had a graph, something that looks like this, I don't know, what does the area under this curve equal? That area is equal to the change in momentum. So you might see a graph like this on the AP exam where they say there's some pulley that's rotating. Here's a plot of its torque, the torque acting on it over time. Find the change in momentum. You have to realize you look at the area under the curve, and that's equal to the change in angular momentum. Just like how we used to do force versus time graphs and how the area for those was the change in momentum. Okay, so we have our same impulse equation now with the cousins. That's not too bad. Part C, conservation of angular momentum. Now we're really getting into what the AP exam is going to focus on when they're asking questions. These are the most common questions. So we'll look at what this means, and we'll look at a couple of examples. So, for an object or a system of objects, as long as there are no external torques, no one slapping the object that's spinning, as long as there's no external torques on the single object or the system, the total angular momentum should stay the same. So as long as this is true, no net external torque, maybe they should say external, well, the momentum you have in the beginning has to equal the momentum you have at the end. Similar to energy conservation, but of course the equations are different. Momentum is conserved. Well, let's look at an example, and this is really the classic angular momentum physics example. We have an ice skater, and imagine this ice skater, she's spinning around, rotating around, all right? And then if you've ever watched the Olympics or something on YouTube, when they pull in their arms, when they pull in their legs, all of a sudden they start speeding up. When an ice skater wants to spin faster and faster and faster, they tuck in their arms, they tuck in their legs. Let's understand why tucking in their arms and legs makes them spin, makes them rotate with a higher speed. Well, pulling in your arms and legs, that's not applying any kind of outside torque, all right? We're just looking at our person, that's our object. So if someone isn't walking up there and pushing on them, no external torques, so the momentum should be the same. The initial momentum should be the final. I'm going to use I and F just because that's what they have here on this diagram. Of course, we might use L naught equals L. Doesn't really matter. So the initial momentum of this skater, well, what's momentum equal to? That rotational inertia of the skater times omega. So their initial rotation times their initial angular velocity, that must equal I times omega final. Okay, well, hold on. This alone doesn't seem to prove to us why you're speeding up. You have to recognize, what is I based on? There's some form of mr squared. You know, there's probably some weird coefficient, but this isn't really a solid object. I don't know what it would be. So let's just focus on the mr squared part. We're not doing any plugging and chugging. We're just looking at how it compares. Well, here, the person's arms are spread out. So they have some initial distribution of that mass. So I'm going to actually label that Ri times that omega I. Well, when they tuck in, obviously their overall mass isn't changing, but now their mass is closer in to that axis of rotation times omega F. Well, which of these two R's is larger? Ri is bigger than Rf. So let me keep going with this equation. The final speed of that skater, well, we see these masses cancel out. What I have is Ri squared times their initial angular speed, angular velocity, divided by Rf squared. So if Rf is smaller, if this value is getting smaller and smaller and smaller as they tuck in, this value must be getting bigger. That's why that skater is speeding up. If your momentum needs to stay constant, well, if your radius is getting smaller and smaller, less and less, the speed has to be getting more and more. So this is the main idea. Here's kind of my summarizing sentence. Since her mass is closer to the center when she tucks in, the rotational inertia at the end is smaller than her rotational inertia in the beginning. So that final angular velocity must be larger. You tuck in your arms to spin faster. This is kind of the math proof, but conceptually, while tucking in your arms decreases your rotational inertia, these two sides of the equation must be equal. So if this side is getting smaller, this must be getting bigger. Okay, we could explain it mathematically with an equation proof, or explain it with the ideas of conservation of angular momentum. Okay, one more example. This is kind of like an angular collision, then we're going to be all done. I have right here two spinning disks. Okay, in fact, actually here I just have one spinning disk. This one's going to start at rest. Omega A initial starts at 0. So two disks are supported. It's kind of like if you've ever seen like the routine of balancing plates. So imagine I have this disc that's spinning, but it's attached to this metal support. Okay, and this whole thing is twirling around and around and around. Same thing, this one's kind of inverted, but we have this disc with this metal rod attached to the middle. This one, though, is not spinning to start, but B, cylinder or disc B, is rotating. Okay, well, A gets lowered down. It's not spinning, but we lower it down, and we assume they just clamp together. There's no grinding, there's no slipping, they just instantly lock into place. In fact, old cars have something called a clutch, all right, and a clutch is doing something very similar when we're changing gears, but we won't get into that. Okay, but we kind of have a collision going on. Just like how we would use conservation of momentum for collisions in linear motion, we can use conservation of angular momentum for angular collisions. Let's just see how to apply that. Let's see how we would do that. I'm going to use L0 and L. The momentum in the beginning, I have a system. So if no one's interfering with these two objects, the overall momentum should stay the same. My initial and my final. Now I'll use my L0 and L. These two things should be equal. What things might have momentum? LA might have momentum in the beginning, and LB might have momentum in the beginning. That equals the momentum of the two things. This is like an inelastic collision. They now are going to spin as some object, and we're going to try and write an expression. So I'm going to go right here. What's LA? What's the initial angular momentum of A? Well, it's 0. The initial angular momentum of B is going to be IB, that rotational inertia, times its initial angular velocity. Now, to be honest, we might have to worry about direction, because if A was spinning clockwise and B was spinning counterclockwise, angular momentum is a vector. We would have to take into account plus or minus. Okay, but this starts at 0, so I'm not really going to worry about plus or minus here. We could just define this direction as the positive. Okay, well, at the end, they combine. For linear momentum, we would add up the masses. We're going to do the same thing. We're going to add up the inertias. Inertia A plus inertia B equals some final rotational angular velocity. Well, so how could I solve for that final angular velocity? That would be IB times omega B naught. So the rotational inertia of A, and if we're doing a math problem, of course, they'd have to give you the rotational inertia equation for a spinning disk, okay, times whatever its initial speed was, divided by the combined rotational inertia of those two things. I know this looks weird, it looks complicated, and I know I'm not plugging in any numbers, but we did the exact same thing, essentially, for linear inelastic collisions. We added up their momentums when they were separate, they collided, they stuck together, so they acted as one object, so their total inertia was the two things added together. We could solve for that final velocity, this right here, omega prime, of the two stuck together. Okay, we'll get some examples with these in the next couple of classes. Thanks for watching.